Eu acho que está gravando agora.
Ok, então, bem-vindos a mais uma edição do nosso seminário Fique em Casa de Geometria Algébrica, também conhecido como BRAG. E é um prazer anunciar essa semana. O nosso palestrante vai ser o Jorge Vitório Pereira, nosso colega do IMPA, e ele vai falar sobre Miyaoka's algebraicity, criterion and variations. Obrigada, Jorge, por aceitar a palestra. E antes de começar, queria pedir para todo mundo colocar o seu microfone no mudo. Please, I ask everybody to mute their microphone. E Jorge agora tem a palavra.
Okay, thank you very much. So this is my first experience with this online talk, so please apologize any oddities that you may find through the exposition. So I would like to take this opportunity to discuss this Miyaoka's algebraicity criterion and say some words about a new proof of a part of this result by the end of the talk. But I will try to discuss some of the developments that this theorem had in the last years, and that's it. Okay. So the general problem that we would like to discuss, where this somehow this theorem gives an answer, is when are all the orbits of a given algebraic or rational vector field algebraic? So you can also pose this problem in a more general setup. You can ask when are all the leaves of a foliation on a projective manifold algebraic? I will define these terms later on, but let me just, I think most of you are already familiar with that. But let me emphasize that foliations, even very simple foliations defined by very simple in the naive sense, algebraic differential equations can have quite complicated and highly transcendental leaves. Even if they are defined by an algebraic object, the leaves are created through the means of integration. So you start with something algebraic, but end up with something transcendental. So let's, this is one example of a transcendental leaf. So here you can see this, this is a drawing, I tried to draw this Loch Ness monster, which is a complex surface, which is topologically a plane with infinitely many handles attached. Of course, this is a much nicer drawing than the drawing on the right is much nicer than on the left. Okay, so this is the typical leaf of a logarithmic foliation on P2 for those who know what they are. Then this was shown by Diego Guzman in his PhD thesis at IMPA. Good. It's not a new problem. It's a very old problem. And I like very much a result on this subject by Abel, who looked at this kind of... do you see a pointer here or no? Who looked at this differential equation, dy over the square root of this polynomial equal to a dx over the square root of this polynomial. And this is he proved, or he studied essentially the one forms or the foliations defined by one form dx plus a dy on the square of elliptic curve. And he characterized it completely for each values of a. This object has all leaves algebraic, and he proved that this happens only when a belongs to the endomorphism ring of E tensor by Q. It's funny that first time that I met this result, reading a book by the history of mathematics, of analysis in the 19th century. And the author, I'm sorry, I tried to remember the name of the book and the name of the author, but I couldn't. But essentially, he says that it's at this point that Abel or the mathematicians recognized for the first time complex multiplication. So it's essentially the origins of complex multiplications are already related to this this problem from differential equations. Okay, so let me say what are these objects more precisely, at least in our context. So foliations, will always be considering algebraic foliations. So I will see these as objects living on projective manifolds. Oh, sorry for the misprint here. So a singular foliation is just an object defined by a coherent subsheaf of the tangent sheaf, which is integrable in the sense that it's closed under the Lie bracket. And we also impose these other conditions to avoid apparent singularity. So we ask Tf to be saturated inside the Tx. In other words, we want the co-kernel of the inclusion to be torsion-free. So the locus where this co-kernel is not locally free is the singular locus of the foliation, and essentially by being saturated implies that it has codimension at least 2. Okay, and it will be not extremely relevant for this talk, but the canonical bundle is just the determinant of Tf dualized. And away from the singular set, the canonical bundle are the differential forms of top degree along the leaves of F. In Abel's result, the foliations in questions all have trivial canonical bundle. So what the results that I want to discuss today all go in the direction that when Tf or Kf has some negative, or Tf has some positivity, or Kf has some negativity, the leaves should be automatically algebraic. Let me just mention that in this previous result, you see some influence of arithmetics into the problem. And while the results which I'm going to discuss today essentially show that under strong geometric assumptions, you can give strong answers to that problem. Okay, so what is this Miyaoka's algebraicity criterion? So it's a result from '87, which appears in this very nice and very deep paper, Deformation of Morphisms Along Foliation Applications. And essentially, this works with this hypothesis, generic positivity of the tangent sheaf. I will not, I don't expect you to read this slide in particular, as I'm going to discuss in more detail the next slide, where probably things are clear. I just want to say that he had this hypothesis, and what he was able to conclude was that the leaves of the foliation, so the leaves are these transcendental objects constructing by integration, they were not necessarily algebraic, but had a strong algebraic feature. They were ruled by rational curves. So in the sense that through a general point of each of these leaves, you have a rational curve completely contained in it. And this result was not a result of foliation theory. He was not interested in foliation. He was not, his main motivation was not the study of the question of algebraic integrability of foliations, but he was instead trying to control some terms in Riemann-Roch formula for free folds in order to prove the non-vanishing theorem, which says that some power, if you have a projective free fold of which is not unruled, some power of the canonical bundle has sections. Okay, so this was a very important step in the proof of this abundance conjecture for free folds, which in higher dimensions is still a conjecture. And this paper is very beautiful, has a lot of deep and interesting ideas, influenced me a lot, but I don't understand it completely. It's very hard to read. On the other hand, but I keep going back to it. I think the first time I look at it, it was already 20 years ago. I plan to return to it periodically, and every time that I return to it, I learn something new. I'm planning to do it again soon. But there is much clearer picture was drawn by Scheffer-Baron 5 years after, or 4 years after, in this paper, which appears as a chapter on this book where this abundance or the abundance for threefolds is reviewed. And he formulated perhaps in a more clear and geometric way. Let me try to explain how it goes. So let's start with Tx, the tangent sheaf of projective manifold, and let's take a subsheaf E of this sheaf. And let's assume that its determinant intersects positively one curve. Then the statement is that there exists a saturated subsheaf F contained in Tx, which still intersects positively a curve, and there is a rational curve M through a general point of X such that, which is smooth at X, it's tangent to this foliation, to the saturated subsheaf, and it has a certain bound on the degree. And so let me just give an idea how this result can be proved. You take F to be the maximal destabilizing sheaf of E and reduce F modulo P. And stability and positivity of F implies it is closed under P powers. So in characteristic P, when you are working characteristic P, you have a new operation on vector fields that on derivations, if you want, if you iterate a derivation P times, you still get a derivation, not a higher order differential operator as in characteristic 0, essentially because of Newton's formula for Newton's formula for binomial coefficients. And in characteristic P, there is also another feature that P-closed foliations are, in the certain sense, algebraically integrable, and it's quite easy to construct the leaf space or construct the quotient of xf of x by f. Essentially, the key is to consider x by f at least over affines to be the spec of the ring of first integrals, the ring of differentials which are annihilated by all the sections of df. And he is able to go down to this leaf space, apply a variant of Morris bend and break argument, produce rational curves tangent to F in characteristic P, an off-bounded degree, and he concludes by lifting these curves to characteristic 0 by means of Hilbert scheme, a simple Hilbert scheme argument. So that's how it goes. Of course, it's impossible to understand this proof in such short outline. But what I want you to keep in mind is that somehow to prove that result, he passed by a construction of an auxiliary space, X over F. In fact, infinitely many such auxiliary space. He has to do it one for each P. And arguing with that space, you can conclude. Very good. So this was the state in the 90s, and in the beginning of the turning of the century, the turning of the millennium, simultaneously there appeared somehow clarifications, more geometric versions of this argument, of this statement, one by Bogomolov-McQuillan, another by Jean-Benoit Bost. So Bogomolov-McQuillan proved that if I have a foliation such that, and a curve, such that I forgot to stress here is that this curve C, I didn't specify, so it's not one fixed curve. So this curve C, it belongs to a covariant family. It must be the kind of curve that we use in meta-Ramanathan theory, because we want to test stability on this curve. So it appears essentially as some curve cut out by sufficiently high powers of ample divisors. So it's not one curve, but a family of curves covering the whole variety. Okay, so here the improvement in this statement by Bogomolov-McQuillan is that now the curve is fixed. We are talking about only one curve. And we are assuming that the tangent of F restricted to this curve is ample, as positive as possible, if you want. Then, through all points in this curve, C, there exists an F invariant rationally connected subvariety Vx of dimension RC. R is the dimension of the foliation along C. You can think that C is away from the singular set of F. No need to. There is a second part which I'm not reproducing here because it's not my intent to discuss it, but essentially that this rationally connects variety. It has a certain bound on the degree of that. And using similar arguments, the statement's not so clear if you just compare the statements, but essentially the same ideas were there that appeared at the same time in this paper by Bost, which were, I think, conceived around 2000, so somehow simultaneously a similar statement. I will not enter in detail in the statement of Bost, but let's say that part of the argument is essentially the same. What I have to stress is that in Bogomolov's Macquillan theorem, this shows not only that the subvarieties, that leaves are algebraic, but also rationally connected, while Bost didn't address this issue. So he didn't say anything about rational connectance or not of the leaves. So this, the theorem of Bogomolov-Macquillan is the main tool for the proof of the cone theorem for one-dimensional foliations with canonical singularities on projective varieties. So this is the starting point of Mori's theory for any kind of object. And while the motivation for Bost was completely different, essentially he had a much more subtle result concerning an arithmetic criterion for algebraicity of leaves. And this is somehow, it's the simplification, the geometric counterpart, which is much simpler than the arithmetic result he gave here. Okay, so let me try to sketch the proof, or at least the proof of the algebraicity part of Bogomolov-Macquillan argument. So we start with here a product. We take the curve C and the variety X, and let's form a diagonal embedding of C in C times X. So this is what is called gamma here in this picture. And we are going to construct a germ of analytic variety, a priori analytic variety, containing this curve gamma. So the idea is that for each point of C, I have one copy of X here, and through this point of C, I add a germ of leaf of F passing through that point in the fiber of over that point here. Okay, so these are geometric constructions. If you write down, it's quite easy to write down equations, and if you assume that this curve C does not touch the singular set, it's clear when you write down equations that this variety, analytic variety F, is smooth and contains gamma. And moreover, the crux to this construction is that if I denote by sigma this diagonal embedding, then the pullback of the normal bundle of gamma in F is the tangent bundle of F in C. And we have transformed a problem about foliations, about leaves of foliations, to a much more natural problem. It's about a problem now about curves, where we have an assumption on the normal bundle of that curve contained in formal or analytic subvarieties. And if, let me write down some notation. If I write L, I choose L, an arbitrary line bundle, denote by Fm the mth infinitesimal neighborhood of gamma inside F, and we let F hat be the formal completion of this F along gamma. Then, this is borrowed from Bogomolov's Macquillan paper, we can consider this natural exact sequence. And we see that for L large enough, or for M large enough, sorry, since we are assuming that this guy and the normal bundle, which is the tangent bundle, is ample, this guy for M large enough, so n bigger than a constant times n, this will be 0. And so essentially says that nothing, no new information appears, and we can use this to compute or to estimate the H0 of restriction of L tensor N to the formal completion of F along gamma. And what you get is that this is bounded by a constant times N to the power R minus 1. And if we think a little bit about this, this implies that this guy, F hat, or at least the Zariski closure of F hat, has dimension at most R plus 1. So again, no dimension at all. So this F hat, or this F that we constructed from the beginning, is a piece, it's a small open subset, analytic open subset of an algebraic variety of dimension R plus 1. So remember that R is the dimension of the leaf, the dimension of the foliation. And then you can just recover an algebraization of each of these small pieces by intersecting the Zariski closure of F, which we know has dimension R plus 1, with a fiber. And this shows the algebraicity of fibers. So this is a very elegant and very nice argument, and it's quite amusing intellectual exercise to compare and see what this has in common with Miyaoka's Scheffer-Baron's original arguments. And at least there is one thing in common that I can see, is that both arguments rely on the construction of auxiliary space. So in the first case, we had to construct, to pass to this quotient, and to pass to positive characteristic and consider the quotient of the variety. And in this case, we construct this, this surface F, which is somehow is also an auxiliary construction. What I would like to explain and to share with you is an extremely simple proof that I found of part of this statement. I will prove only part of this. Only part of this, but which does not, it's a more direct proof, does not rely in any auxiliary space. But before doing that, let me just mention that this result, and this argument has been greatly generalized by Campana-Paul in the very, very recent paper in 2019, and where they somehow can refine and keep elements of both proofs that we saw. So now he just have a foliation on a projective manifold. And now we take a movable class. Movable class is a numeric incarnation of this concept of covering family of curves. So you don't need to actually have a covering family of curves. You only have a cohomology class which behaves like that. And under some assumptions, the natural assumptions, if you think about it on the slope of F with respect to this minimal class, they can prove that the leaves of the foliations are algebraic, and that the closure of a leaf is rationally connected. And again, the point is that to prove that the leaf is algebraic, the strategy is just to realize that this previous argument can be done replacing a C by the whole X. You don't want to use C, but you replace it by the whole X. And you consider exactly the same constructions. Over each point of X, you put the germ of leaf through that point. And you have to refine all these computations and show that you can get the same conclusion by replacing the assumption on the normal bundle by ampleness of the normal bundle by this slope positivity with respect to a movable class. So it's technically very involved, but the key idea is essentially to consider this, what is called the graphic neighborhood. And this has a very nice corollary. If KF is not pseudo-effective, then F is unruled. And this result, again, was not the main motivation for this study. What they end up studying this result also to study a very deep problems with, Vivex conjecture, which asks for the existence of a relation of the variation moduli of a family and positivity of the base, or at least or positivity of an orbifold version of the base. Very good. So what I would like to share to you is this result, which is a particular case of all that we have seen before, but which comes with a very, very simple proof. So I will restrict myself to a foliation by curves. So so far, my arguments do not work for foliations of arbitrary dimension. It only works for foliation of dimension 1, foliation by curves. And what I want to give is a general proof, a direct proof, essentially from the definitions, that if the general leaf of this foliation is not algebraic, then the canonical bundle is pseudo-effective. Okay? So let me recall what is pseudo-effective. So this canonical bundle is a line bundle. So we can look in the Néron-Severi group, the positive cone generated by classes of effective divisors. And we are saying that the line bundle is pseudo-effective if its class in the Néron-Severi group lies in the closure of this effective cone. Okay? So what I want to give a proof of this statement by constructing a sequence of effective divisors approximating KF. That's what I want to do. And for that, since my foliation is, the general leaf is not algebraic, I can choose one of them. And I can choose an ample line bundle on X. And the point is that if I restrict sections of powers of this ample line bundle to L, then I know that this will grow at least quadratically. So it will grow with the order equal to the dimension of the Zariski closure of L. And since I'm assuming that it's not algebraic, so this Zariski closure has dimension at least 2, and so we have something like this, essentially, at least for large K. So I can choose a vector space Vk contained in the H0 of x, L power k of dimension k squared plus 1, at least if k is large enough. And I will ask the restriction of Vk to L, to the leaf, to be injected. So of course, I can do that. Now, by my definition, a foliation on F is defined by a subsheaf of Tx. In this case, we are assuming that this guy has rank 1. And so I can see this subsheaf as a section of Tx tensor, the dual of Tf, which in rank 1 case is just Kf. And so my foliation is defined by a twisted vector field with coefficients in Kf. If I just now take S0, Sk square, a basis of this Vk, and form this Wronskian determinant, I know, since the restrictions to Vk is injective, I know that this determinant is non-zero. It's just the criterion for algebraic or for C-linear independence of functions along a curve. Very simple, and you compute, and you see that indeed this is I'm kind of abusing the notation and I'm writing local expressions for this thing. But if you see what kind of object we are defining, we are indeed defining a section of L tensor k squared plus 1. L, so S0 is a section of L tensor k. I have here k squared plus 1 rows, and so this is the contribution that comes from this term. And now the contributions which come from the cocycle defining V is indeed k squared plus 1 k squared over 2. And so here I have this, right? So the contribution that comes is 0 plus 1 plus 2 plus k squared. I get this number. And this is essentially now so this is a non-zero section of here. So since this thing goes with order 4 and this goes with order 3, if I normalize, I see that KF, or at least, yeah, KF is a multiple of effective Q divisors. Indeed, they are coming from here, right? And so that's the proof. That's the statement. I would really like to find a way to stand this argument to obtain at least this corollary of Campana-Pound, but at least to prove that if there is no algebraic subfoliation of F, I would have that KF is not so effective. But so far, I don't know how to do that. And I would really appreciate if any of you had ideas on how to do that, but that's it. Well, I plan to give a 40-minute talks. I finished in 36 or 30, but that's it. I don't think we can keep concentration much longer than 40 minutes in this online talk, and I will stop. I'll stop here.
Thank you, Jorge. Let's thank Jorge for the talk. So are there questions or comments? So I have a question. So what about the rationally connectivity? Is there any way that you see to use, for instance, suppose that the leaves are not rational or not unirational or not covered by rational curves, to be able to adapt this argument in this case, like using the curves instead of the...
I don't see how to do it. Even in the case, even to prove, even the case of dimension 1, my argument doesn't show that the curves are algebraic. I don't have a clue how to prove using this kind of argument that the leaves are rational, sorry. I think it's, yeah, I have no idea if it's possible to do something like that. Of course, something in this direction would be fantastic, right? Because if you just push to the limit, this kind of, essentially, doing that, you would be able to prove, I think, Buxon, Desmailles, Paul Peternel by algebraic methods. This is, again, the same problem. So there is this result which says that variety is not ruled if and only if the canonical bundle is pseudo-effective. So this variety is a foliation with one leaf. And to be able to detect rational connectance by means of what this object is at the end is a symmetric differential. To detect them by means of symmetric differential or jet differential. To detect it by means of jet differentials in a form would essentially bypass this deep arguments of Buxon, Desmailles, Paul Peternel. But yeah, that would be fantastic. See, because it's really important, it's really hard problem, right? To show effectiveness of some bundle, or even to show the effectiveness. It's in general it's hard. Here we have a lot of luck that this naive construction gives these sections. But yeah, no, I have no idea how to prove rationally connectors of leaves. But I do have hope to be able to deal with the case of higher dimensional leaves, higher dimensional foliations. And somehow I would like to detect, to show that if I have a foliation which is purely transcendental, through a general point, there is no algebraic subvariety tangent to a leaf, I would like to be able to prove the same statement.
Mm-hmm.
But again, I'm proving things which are known. There's the statement, there is nothing new to this statement. What is new is the proof.
So another question. So what would be the new statement that you would like to prove using this this approach?
No, I'm not ambitious guy. I just the point is that it was really hard for me to understand this Bogomolov, McClellan, Miyaoka, Scheffer-Barron argument. I taught courses at IMPA about foliation theory for more than 10 years, where I explained this theorem, and now I think I understand. But at the beginning, it was kind of odd. And this construction is something that I did in my thesis. And I find it's funny. I find it it's a very short proof. And I don't know. What would be, if you want to dream, it would be nice if I could do the other way around from what Boss did. Because Boss arrived at this algebraicity criterion by transforming an arithmetic argument into a geometric argument. To have an arithmetic version of this argument, probably would say something new about the Grothendieck-Katz conjecture or things like that. But yeah, that's wide guess. But yeah, no, I don't want to prove anything new. I want to prove at least understand that one. Well, it's a one-slide proof.
Are there more questions? So if not, let's thank Jorge again for his talk. And we meet again 1 week from today. And I forgot who the next speaker is.
It's Thiago.
Okay, Thiago, you're right.
Yeah.
So stay safe, stay at home, and see you next week. Thank you, Jorge, again.
Thank you.
Okay.